Alright, let me start by sharing the screen. I hope my screen is visible, right?
Yes, sir.
Fine. So, या संकेत, आपको कुछ पूछना है क्या? आपने हाथ उठाया।
यस सर। यस सर।
हाँ, बोलिए।
सर अभी करंटली मैं थर्ड ईयर में हूँ।
हाँ हाँ।
जीटीयू के अंडर में कॉलेज में हूँ और मैं
किसमें हो?
एनालॉग का जीटीयू के अंडर गुजरात
ओ,
टेक्निकल यूनिवर्सिटी।
अच्छा, ओके।
ओके, तो मैं करंटली ये कोर्स कर रहा हूँ पर इस कोर्स में जो सर के लेक्चर्स में देख रहा हूँ ना,
हाँ
उससे
हाँ।
कई सारे डाउट्स और ऐसे कई सारे वो सोल्व नहीं हो रहे। मीन्स क्या, सर सिर्फ डायरेक्ट थियरी और डायरेक्ट कोई इक्वेशन लिख रहे हैं पर क्यों कैसे हो रहा है वो खुद थोड़ा समझ में नहीं आ रहा है। तो उसका कोई आप सजेशन कर सकते हो कोई दूसरा, या
अच्छा
क्योंकि कई सारे असाइनमेंट के क्वेश्चन भी है वो सोल्व करने में भी दिक्कत आ रही है, तो फिर
अच्छा, ठीक।
ऑनलाइन हेल्प लेनी पड़ती है इसका सब
ठीक
कुछ।
है, ठीक है। देखिए, आप ऐसे तो अगर आपको जो भी कंटेंट है उसको समझने में दिक्कत अगर आ रही है, तो आप वो मुझसे यहाँ पे पूछ सकते हैं, ठीक है? मेरे से आप इन इन सेशंस में पूछ सकते हैं मेरे से, या फिर जो भी जो दूसरे ट्यूटर हैं एक और, ठीक है, हैंडल, उनसे मतलब हम दोनों से आप पूछ सकते हैं ये सारे सवाल, जो भी आपको इस कोर्स से रिलेटेड डाउट्स हैं, ठीक है? अगर आपको उस वक्त मतलब इतने समय में अगर आपको डाउट्स पूछने में दिक्कत आ रही है, अगर आपसे आपके डाउट्स क्लियर नहीं हो पा रहे हैं, तो फिर आप एक काम ये कर सकते हैं कि आप ये इस कोर्स के फोरम पे कुछ अपने डाउट्स पूछ सकते हैं, ठीक है? मतलब आप मेरे को ये जानना है कि आपके डाउट्स किस तरह के हैं। आपने कभी मेरे से डाउट पूछा नहीं है कोई भी अभी तक, जो भी आपको कंटेंट समझने में दिक्कत हो रही है उससे
यस,
रिलेटेड, तो या तो
उसमें
आप
सर
मुझसे।
वो इक्वेशन कभी बनाने में प्रॉब्लम होती है। मीन्स क्या है, जो नॉर्मल रजिस्टर दिए होंगे तो वो हो जाता है, पर अगर वो कॉम्प्लेक्सिटी में आएगा तो वो बहुत सारे प्रॉब्लम्स हो रही है। मीन्स फिर वो
ओके।
ट्रांसफर फंक्शन हम लिखते हैं तो ट्रांसफर फंक्शन में पोल जीरो का पता चल गया है, पर
हम्म।
उसमें वो फ्रीक्वेंसी वाला कॉन्सेप्ट है और फ्रीक्वेंसी के ऊपर से कई सारा ऐसा कॉन्सेप्ट है कि क्रो गेन मार्जिन है और क्रॉस ओवर फ्रीक्वेंसी है, वो ढूंढने में
हाँ, बट अभी
थोड़ी।
अच्छा अच्छा, वो फोर्थ वीक में है, राइट? सॉरी, थर्ड वीक में है वो कंटेंट, राइट? थर्ड वीक और फोर्थ
ओके।
वीक
और
में है सब।
ओके, और वीक टू में अगर देखा जाए तो वीक टू में वो बॉडी प्लॉट वाला है, उसमें थोड़ी प्रॉब्लम हो रही है।
ठीक है, आज आज हम लोग वही डिस्कस करेंगे, ओके? आप मेरे को जब हम बॉडी
Sir,
प्लॉट पे मतलब, हाँ, यस।
sir, I am facing difficulty in actually solving for mid-band gain and all such things, sir. Like when we are given a huge RC network with lots of resistors and capacitors, I'm unable to work it out.
ओके ओके।
और सर
ओके, विल ट्राई टू
वीक
सी, विल ट्राई टू लुक एट सम एग्जांपल्स, ओके? विल ट्राई टू लुक एट सम
ओके,
एग्जांपल्स।
और सर वीक वीक टू में सेकंड नंबर का क्वेश्चन और 8 नंबर का क्वेश्चन में प्रॉब्लम हो रही है असाइनमेंट्स।
अच्छा, वो हम लोग देखते हैं, ओके? हालांकि असाइनमेंट के जो भी क्वेश्चंस हो गए वो हम डिस्कस नहीं कर सकते यहाँ पे, ओके? उस तरह के क्वेश्चंस हम
सर
डिस्कस कर
सबमिट
सकते।
हो गया है सर, असाइनमेंट का आंसर्स आ गए हैं तो
सो
सर।
असाइन
ओह,
हाँ।
अच्छा अच्छा, ओके ओके, इन दैट
वीक
केस वी कैन श्योरली डिस्कस, ओके? इन दैट केस वी कैन
वीक वन।
श्योरली डिस्कस, इट्स नॉट अ प्रॉब्लम।
ओके, वीक वीक वन
ठीक
और
है,
टू के आंसर्स और सब कुछ आ गया है इसलिए।
या ठीक है, फिर हम लोग डिस्कस करते हैं, ओके? आप
ओके।
घबराइए मत। आप मेरे को बताइएगा अपने मतलब ये जो सेशंस हैं इसमें आपके डाउट्स क्लियर करने के लिए ये सेशंस हैं, ठीक है? मेनली यही पर्पस है इन सेशंस का। तो आप मेरे को अपने डाउट्स बताइए, ठीक है, संकेत? सो आप
यस
मेरे
सर।
को अपने डाउट्स बताइए। जब हम डिस्कस कर रहे होते हैं आप मेरे को बताइए कि आपको किन चीज़ में प्रॉब्लम्स है, तो फिर वो पर्टिकुलर टॉपिक हम डिस्कस करेंगे, वरना फिर मेरे को नहीं पता कि किन चीज़ों में
यस
किन
सर।
किन प्रॉब्लम है, right? So here's what you all do, Vasanti, right? If you have a certain doubt, just you have to tell me, okay? Otherwise I'll not be able to understand I'll be preparing a very general topic for discussion. Okay, but if there are certain doubts which are very specific to you, then you have to come forward and speak it out, right? Only then can I understand. So
Yes,
let's
sir.
hope today I'll be able to clear all of your doubts. Okay, I'll be covering. So whatever I'll be covering, I'll be covering week two content today. Okay, so if there is any doubt in the this so basically uh, sorry, yeah, so these are the things which I am going to cover today. So just tell me, looking at the topics here, do you have any doubt in any particular topic here, all the people who are present
Sir,
here?
I was thinking, sir, like in the input impedance of the op amp, it is very high. Sir, then how will we have bias current? This concept is not clear to me.
Acha, okay, okay, I'll address that. So I'll just quickly note everything down. Okay.
और सर वो नॉन नॉन आइडियल ओपीओपैम होता है ना, तो उसमें वो इक्वेशन बनाने में बहुत प्रॉब्लम हो रही है। मीन्स आइडियल का तो डायरेक्टली हो जाता है और बॉडी प्लॉट में हो रहा है।
So forming equations for non-ideal op amp, right? That is one. The other one is so what is the, or rather, how can we have bias currents in the op amps when the input resistance is very large, right? These two are the doubts, right?
सर
Yes,
वो
sir.
बॉडी प्लॉट वाला भी है तो
हाँ, अच्छा. So body plot, okay, tell me
मैं
specifically what is the doubt in body plots? Is it
एक
like overall?
क्वेश्चन पूछा गया था कि बॉडी प्लॉट है और अपर 3 dB फ्रीक्वेंसी और गेन फैक्टर फाइंड करो, तो अपर वो 3 dB फ्रीक्वेंसी और लोअर 3 dB फ्रीक्वेंसी होती है ना, उसमें थोड़ा डाउट
Okay,
है। फाइंड
so
कैसे
basically
करें सर, समझ में नहीं आ रहा।
the F, or rather 3 dB frequencies, looking at the body plot, right?
यस सर।
Body plot. Acha. Anything else?
Sir, then mid-band gain when given a huge RC network. Sir, like gains कैसे? Sir, कई सारे gains है ना?
Okay, fine. You can speak in English. I am comfortable with English. It's just that Sanket is not comfortable with English, so I that is why I have to move on to Hindi. Anyway, you can continue. So you have difficulty in finding mid-band gain when you have a large RC network. That's what your doubt is, right?
Ye- Yes, sir. Yes, sir.
Okay, let's see. Finding the mid-band gain for a large RC network. Is it all? Is it exhaustive? The set of questions here.
Yes, sir.
Okay, fine. So then, in that case, I'll not cover all these things, right? The first thing here, which I was covering that day. So I'll just not consider this. Okay, I'll move on. I'll straight on move on to the doubts here, which people have. But before that, as a formality, let me just introduce myself. Alright. So basically, this course is a MOOC course, analog circuits, and it is being offered by NPTEL. The instructor for this course is Dr. Jayanta Mukherjee. My bad. The instructor for this course is Dr. Jayanta Mukherjee. He is a professor in the Department of Electrical Engineering at IIT Bombay. Myself, I am Mayank Anupam. I am a PhD scholar at IIT Kanpur in the Department of Electrical Engineering. Fine. So today, basically, this is a remedial class, or basically a class which is happening on this day, on Saturday, because we were unable to have a session on Tuesday, right? So we are having some difficulties, network problem at my side. So that is why the class is shifted to today, rescheduled to today. So today we will be covering the content that was taught in week 2, okay, and the rough and the points and the rough outline of these of the week 2 lectures was that we discussed non-idealities, right? I mean the instructor discussed non-idealities related to an op-amp, namely finite gain of the op-amp, finite bandwidth of the op-amp, and slew rate. Okay, we also discussed about two other very important non-idealities: offset voltage in op-amp, and the bias current in an op-amp. Okay, then he moved on to the most important, I would say most important part of this body plot is to me is the most important part of related to analog engineering. Okay, we'll come across this all the time, body plot. So this is one of the most important thing. So we saw what is body plot, and then we went on to find the frequency responses of various circuits, how to find it, and how to represent it with a body plot. That is what we did. So that day I was talking about slew rate. Okay, so should I talk about slew rate or not, or are you guys comfortable with it? So I need some input from your side.
So can you talk about it? You can explain more.
Okay, fine. So I'll quickly talk about it. Slew rate. Uh, so basically, what do you understand by slew rate? I mean, that day also we talked about it. Basically, the output will not respond to the input immediately, isn't it? That is what we understood roughly by the by this term slew rate, isn't it? If these two are the input, I mean this is the input, and let's say this is V in. If this is V in, and this is V out, and let's say it has some finite gain. AV is equal to the gain from input to output. Okay, let's say that is some finite number. Let's say that's 60 dB or so. Okay, we know that the rough representation of this is what is like this, right? So if you have two inputs here, okay, then basically, or rather, if this is V in, okay, and here we have connected a voltage source like this, then right, this is the equivalent circuit. I mean, this is one of the block level this is one of the representation of the inside of the op amp, isn't it? Is everyone comfortable with this? On a
Yes,
very
sir.
rough level, this is a very rough idea, right? So I will completely ignore the output resistance and everything. I've just taken into account the brute force gain from input to output, that's all, nothing else. So yeah, so in this circuit, if we apply a voltage here, if we apply an input voltage which is a step like this, okay, so what do you think should happen at the output voltage V out? So let's say it is a 60 dB. 60 dB is equal to how much? Is equal to 1000, right? So it's a gain of 1000. Okay. So if you apply a 1 millivolt input here, what should happen at the output here? What should happen at the output? From this circuit, we can understand that this output V out should immediately jump to how much? 1000 millivolt, isn't it? So this is V in. Okay. This is V in, and this is what? This is V out. This is what should have happened according to the op-amp that is presented to you before here. Fine. But what ends up happening is it will not immediately jump. What it will do is it will do something of this kind. It will do something of this kind. It will come here and then it will slowly rise like this. Okay. And why do you think that happens? Yeah, so it is because in actual implementation of the circuit here, I mean this is the block, right? This is the op amp here. When you actually implement it using transistors and everything, you will see that at the output here, you will should use a different color. Yeah, at the output here, you will see some parasitic capacitance. Okay, CP. You will see that there is some parasitic capacitance at the output here. You cannot do anything about it. This will just be present here. This will be there regardless of whether you put it or not, because that is why it is called parasitic. Okay, you cannot do anything. It will just disturb your normal circuit operation, but you have to live with it. You cannot do anything about it. This will be there. You have not explicitly put it. That is why I have denoted it by dots. I mean, not by solid line but dotted lines. Okay, you have not explicitly put it here, but still there it will be there. It will be present here because of how the circuit is manufactured. Okay, is that clear? Is that clear to everyone? Fine. So in that case,
Yes, sir.
yeah, so when this capacitor CP is present here, what it will do is it will for if the output V out, I mean this CP here, it will also appear at this point, right? I should maybe draw another circuit here. So this circuit will look like this. So this is in, and right, this is AV times V in, and then we will have this capacitance at this point here, right? Since it is connected to the output. Okay, so if you have a 1 millivolt input here and you expect what do you expect? You expect a sudden jump at the output, right? You want the output to jump suddenly because 1 millivolt is the input here. The response to this by this circuit should be what? AV times 1 millivolt, right? And AV is 1000, so it should be 1000 millivolt. And this jump here, it should be sharp, right? This is what you expect. But you know that for this jump to be sharp, and this V out, this is V out, right? This is V out. This is V out. So this V out voltage, it appears across the capacitor, isn't it? So this is the capacitor here, and this V out, it appears across it. Is it right? So in that case, if this V out has to jump suddenly, across this capacitor, you know that what is the current if this voltage has to jump instantaneously? What is the current that is going to come into the capacitor? So what is current through the capacitor? ICP is equal to C times dV out by dt, isn't it? Is that fine?
Yes, sir.
Yeah. So ICP, which is the current which is going to be flowing into the capacitor, it is equal to C times dV out by dt. Now, if this for this profile here, for this profile here, what do you think should be the would be the dV out by dt? If the V out is there is a sudden jump in V out, what is dV out by dt?
Sir, 1000 millivolt by dt. Sir, if dt tends to zero, then it will be infinity.
Correct. So it will be infinity, isn't it? Because it suddenly jumps. So dt is infinitesimally small, or rather you can say that it doesn't. It is actually almost zero. So it will be infinity, isn't it? So this says
Yes, sir.
that the current required by this capacitor to make this sudden move at the output for the voltage across the capacitor to change suddenly, it requires infinite amount of current. The ICP has to be infinite. In that small amount of time, a lot of charge has to be flowing onto this capacitor to make this happen, isn't it? Now, this infinite current, who is going to provide this current to this capacitor? If at all the V out has to change at the output, who is going to provide this current? This current ICP is going to come from where?
Sir, from that voltage source.
Like this, right?
Yes, sir.
Isn't it? So you see that this ICP current, basically this current ICP is going to have to be provided by this voltage control voltage source here, right? This voltage control voltage source. Now that is where the problem comes. There is when you actually implement the circuit, when you actually implement the op amp using real transistors, you will see that it has a limit on how much current it can provide at one time. Okay, you will end up means what will happen is there will be a limit to the current that can be provided. Okay, so because of which ICP will probably be less than, always less than some IC, or rather I max. Okay, and that I max will be the limit of how much uh, sorry, the I max will be the maximum amount of current that can be provided by this guy here. Okay, so ICP this basically it will be limited. The current that is going to flow into this capacitor CP, parasitic capacitance CP, is going to be limited by this by the maximum current that is going to be provided by the this voltage control voltage source. And because of which now, if let's say this current is this current is going to be limited, what will happen? Definitely it will not be able to jump, right? This voltage, it will not be able to jump like this. So what will happen? Come on, you have done the hard thing, you have
सर
given all the
फिर
answers, so tell
फिर
me
से
what
एक
will
बार
happen.
Sir, it
रिपीट
will
करो
increase
कि
gradually.
Right, good. So it will do something of this kind. So rather than doing this, it will not be able to do this, but it will do this. It will first do this linearly, it will increase, and then it will do this. Okay, fine. So this is actually, this is what is this 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 phenomenon where the current maximum current is limited, that is going to be provided by the op amp is limited, and because of which the output voltage is rising slowly, okay, or rather linearly. The initial rise would be linear. Okay, sorry, the initial rise here would be linear. Okay, so this phenomenon whereby this happens, this is called slewing. Okay, slewing, this is called slewing. Okay, so did you
Yes,
understand
sir.
the meaning of slewing now? Do you understand what is slew? And the definition, I mean, and the how to find slew rate, so that is actually given in the already taught in the this thing lectures, right? How to calculate slew rate. But I wanted to impress upon you the idea of slewing. How does it happen, and what is the main reason behind slewing? The main reason behind slewing is basically the fact that there is a limit to the maximum current that can be provided by the op amp. Okay, so this you should take away from today's session. You should know what is slewing. If anyone asks you, you should be able to convince them that it is due to this. Okay, due to this important factor. Fine. Okay, so now let's move on. uh, I guess you have already understood offset voltage, right? Offset voltage is clear to everyone. Fine.
Yes, sir.
Yeah. So then we come to the bias current. So there was a doubt, second doubt here. How can we have bias current in the op amp when input resistance is very large? All right. So this is interesting. You see, bias current was actually a very is not actually a very big problem nowadays, because I mean, bias current this bias current is going to be a problem only for circuits which have BJTs. Okay, so later on you will. So do you guys know about BJT, bipolar junction transistor, and MOSFETs? Do you guys have a rough idea anything
Yes,
about it?
sir. PNP
Yes, sir.
and PN transistor.
Correct. So this bias current is going to be mainly a problem for BJTs, okay, bipolar junction transistors, because so how are they? So this is, so come on, what is this? This is base, right? So I have drawn an NPN transistors. So this is base, this is collector, this is emitter, right?
Yes.
Good. So what happens is, the way which BGT works roughly, and you will definitely come to know about it later. Before I move on, let me answer a question asked by someone in the chat section. So Nanu, this the sessions will are actually recorded, and the links are actually provided to you in the portal only. I guess you are able to access them, and there was an announcement also made regarding this. So I guess you will be able to access them. Fine. Coming to the point here. So way BJT works, which you will also come to learn later in this course, is that it requires certain bias base current. Okay, certain biasing base current, and that base current is going to be amplified by a factor beta, and is going to flow here. Okay, that is how it works. So for the current to flow in the main branch here, I mean, through collector to emitter, this current, there has to be a current here, otherwise this will not work. So that is why there is always going to be a current at the base, and uh, like the way that I have drawn it, it also makes it is also very intuitive that you are always going to apply your signal at this to the base of BJT only. Okay, the signal is going to be applied here itself to the base. So that is why there will always be some current that is going to be coming from the input, that is going to be demanded by the input of the BJTs. Okay, so this is what is meant by bias current, input bias currents. Is that fine?
Yes, sir.
Yeah. Now what happens in MOSFET is that MOSFET is a circuit like this. Again, I have drawn what? I've drawn a NMOS here, and this is a NPN BJT. So in this case, this is actually an open circuit. Okay, so the gate, this is actually called the gate, this is called the drain, this is called source, and this is called body. It's a 4 terminal device. So in this case, the body, you can forget about it. I've just mentioned it, but you can forget about it. And most of the times you don't have to worry about body. So let's only consider three terminals here. So the gate and the drain and source. Okay, so this is drain, this is source, this is gate. The gate is actually completely, electrically isolated from drain and source. Okay, what I mean is there is no direct connection between them. Fine, there is no direct connection between these two. So there is actually, gate is actually floating. So there can be no current going to into the gate. The current Ig is equal to 0, or rather almost equal to 0. For your purpose, you just assume it that the gate current will always be equal to 0. Okay, and the current that is going to flow through this, which is Id, is actually a function of the gate voltage. Okay, so Id is a function of Vg. Is that fine? In this
Yes,
case,
sir.
this collector current IC is a function of,
IB.
yes. Okay, so this is how it works. So in this case, the gate current is 0, and in this case, for normal, for your case, for your purpose at least, for your understanding, you just assume that the current is going to be 0. So in this case, the input current is actually 0. Fine. The input current problem, the input bias current, is a problem only for circuits which have BJTs. Fine. Is that clear?
Yes,
So
sir.
Yes,
now
sir.
you might ask if that is, if NMOS is so good, MOSFET is so good that it doesn't have a whole, you know that complexity increases with increasing number of parameters, right? So if this is a base current which is not there in this MOSFET, so why do people still work with BJTs? Why don't we all move with work with NMOS only? So that question is a very valid question. In fact, I also have this question all the time. The answer to this is that BJT is now used in very niche applications. Okay, with very high power or very high uh, frequency operations, we use BJT. Otherwise, we generally use MOSFETs only. Okay, we generally use MOSFETs. BJTs are used for very specific purposes. Fine. So there, it has some very good things to give us. So that's why we use BJT. Now, coming to the question, what is the meaning of how do we have bias currents in op amp when the input resistance is very large? You see, when I say there is a bias current, doesn't mean that the bias current is of very high. Okay, bias current will be very low, very low. So even if you have a very large input resistance, bias current and the bias current will be so low that the product IR will be a very small value. So does that answer your question, Vasanti?
Yes, sir.
I mean, this was the question, right? This was the doubt that you have had.
Yes, sir. I was wondering, like, how does the signal go inside? As if
Oh,
the transistor is actually in some mode of operation, then like when the diodes are like reverse bias, there will be a small current. So this is also something like that.
I mean, yeah, but the rough idea is that, okay. Rough idea is this only. You can have bias current. You have to have bias currents if you are using BJTs, but the bias currents will be so small that you don't have to worry about it. I thought you were worrying about the IR drops. I thought you were saying that maybe the R is so large that I into R, this IB into R will be very large, and it will be, so that doesn't happen. That is how we design the circuits. Anyway,
Yes,
so
sir.
yeah, the next question is what? Coming to the next point is Bode plot, right? Uh, hmm. So someone had a doubt about Bode plots. Bode plots. Let's quickly discuss it. So did you guys understand what is Bode plot? How to plot? How to make Bode plots for transfer function? Do you guys understand how to make Bode plots if you are given a certain transfer function?
Yes, sir.
Let's take an example. I will ask you guys to draw it for me. I will not draw it. Let's take an example. Let's say a transfer function is h of s is given as s minus 2 into, this is not good. Let's say it is 1 plus s by 2 into 1 plus s by 4 divided by 1 plus s by 9 to 1 minus s by plus s by 15, 1 plus s by 20. Okay, let's say it is multiplied by certain number 100. Now tell me, how will you plot, how will you make Bode plot for it? I'll not do it. You have to say, you have to solve it for me. How do you make Bode plot for this?
Sir, we mark the poles and zero frequencies on the axis,
Okay, so
x-axis.
first point is that we have to find out what are the poles and zeros, right?
Yes, sir.
So let's find out. Find poles and zeros. Yeah. So what are the poles and zeros? What are the poles? Come on. This is not difficult.
Sir, 9, 15, 20.
Yeah. It is not 9, 15, 20. It is minus 9, minus 15 and minus 20. Okay.
Yes, sir.
Yeah. So be very specific about that. Don't be casual about that. Fine. So what are the zeros? It is
Sir,
minus 2,
minus 2 and minus 4.
minus 4. Good. Fine. Now, what is the next thing? Now we want to, uh, what do you want to do? Tell me. What is the next thing?
Sir, we mark them on the x-axis
Okay.
and the magnitude of the transfer function on the y-axis.
All right. Let's do that.
Sir, and we replace s with j omega.
That was I was looking for this answer. So that is the most important point. So before making Bode plot, you have to replace s with j omega, isn't it? Correct? So it will be 1 plus j omega by 2 into 1 plus j omega by 4 divided by, oh, I have loss of space here. One plus j omega by 9, 1 plus j omega by 15, 1 plus j omega by 20. Right? Okay, do it now. Oh, why did I make so large? Actually starts right here. Yeah. So I have to, what I have to do? I have to mark these points, right? So let's say this is, so I have to mark minus 2, right? Or 2. What should I do? And what are the, by the way, this is what? This is the magnitude, right? And what should be this? Omega or j omega or minus omega, what? What should be the this? What should be the x-axis?
Sir, omega.
Omega, very good. So tell me, what should be, so the poles are actually -2, -4, -9, -15, -20. So but I have, so should I place them in the left half plane, or should I place in the right only? What should I do? You understand that this is the omega greater than 0, right? So what should I do? This is omega greater than 0, and this is omega less than 0. What should I do? Are you guys confused?
Yes, sir.
Yeah. Okay. You see, it doesn't matter if it is plus or minus. You have to just look at the magnitude of the poles and zeros. Okay. Fine. Just have to look at the what are the what is the magnitude of this poles and zeros. So this is 2. This is 2. Then we have 4. Then we have what? 9. Then we have 15. Then we have 20. Okay. And why are we doing that? Because you see, the way we make Bode plots is that we are trying to find the magnitude, right? We are trying to find the magnitude of the transfer function. We are taking the magnitude of this guy, right? Or rather this guy. We are taking the magnitude of this guy, which means that we are just trying to so I am not going into detail of this. In the lectures has explained this. So the way that we do it, just take the magnitude. So when we take the magnitude, it doesn't matter whether it is plus or minus. Okay, it doesn't matter whether it is plus or minus. So it is very obvious, right? When you take the magnitude of 1 plus j omega by 15 or 1 minus j omega by 15, does it really matter? Both will be how much? Root over 1 plus omega square by 15 square, right? And this will also be 1 plus omega square by 15 square, isn't it? It will not matter whether it is plus or minus. In this case, where is the pole? In the first case, the pole is at minus 15, but in the second case, the pole is at 15, isn't it? Are you guys with me?
Yes, sir.
Yeah. So I guess that answers your question. So don't be confused in this ever again. Okay. So what is the next thing that we should do? I have marked all the points. Yes. What is the next thing?
Sir, find the magnitude in decibels.
Okay. So this is actually very good point. We have to find out the magnitude in decibels. So this is basically in dB, right? And what is dB? What does dB means? You have to do 20 log of something, right? 20 log of mod of, isn't it? This is what you have to do. So tell me, this, let's say this is 0, the frequency is 0. So what is the value of at this frequency 0?
Sir, 100.
Yeah, in terms of dB. In dB, what is the value?
Sir, 40.
Yes, good point. So it is 40, right? So let me just mention mark 40 here. Yeah, what should I do after this? Yeah, so what should I do after this? No, actually did a no, not a mistake, but let's mark 40 here. Okay. And
सर वो 40 किस तरह से है वो समझ में नहीं आया फिर से।
ओ अच्छा अच्छा, देखिए ये जो वैल्यू है यहाँ पे डीबी में लिखना है, राइट? तो जीरो पे एस डी सी फ्रीक्वेंसी ओमेगा इज इक्वल टू जीरो पे मॉड ऑफ एच ऑफ जी ओमेगा कितना है? ये जो एच ऑफ जे ओमेगा है यहाँ पे है ना, एच ऑफ जे ओमेगा यहाँ लिखा है मैंने, इसका मैग्नीट्यूड कितना होगा ओमेगा इज इक्वल टू जीरो पे? जब यहाँ पे ओमेगा इक्वल टू जीरो पुट कीजिएगा तो इसकी वैल्यू क्या बनेगी? हेलो संकेत, इसकी वैल्यू क्या बनेगी?
यस सर।
ओमेगा इक्वल टू जीरो पे इसकी वैल्यू क्या बनेगी? ये चीज जीरो हो जाएगा, है ना? वन प्लस जी ओमेगा बाई टू, वन प्लस जीरो हो जाएगा। ओके, ये भी चीज जीरो हो जाएगा, ये भी चीज जीरो हो जाएगा, ये भी जीरो होगा, ये भी जीरो होगा, है ना?
यस सर।
तो फिर बचा क्या? वन प्लस
100।
हंड्रेड बचा सिर्फ, राइट? तो
यस।
100 × 1, तो इसका वैल्यू क्या बनेगा? 100, राइट?
यस सर।
अब इसको डीबी में कन्वर्ट करना है। डीबी का मतलब क्या होता है? 20 लॉग ऑफ एंड लॉग विथ बेस 10। ओके, लॉग बेस 10 होता है यहाँ पे। 20 लॉग ऑफ
यस
वॉट
सर।
एवर 100 है अगर, तो कितना बनेगा वो? 20 लॉग ऑफ 100 कितना होता है?
2 2 into 20 is 40।
हाँ, 2 × सो बेसिकली इट इज 20 × 2, राइट? तो 40। ओके, सो वहां से आइए 40, ठीक है? अभी समझ आया आपको?
यस सर।
हाँ, फाइन। Yes, what should I do next? What is the next thing that I should do? I have reached till this point. I have, this is 40, right? What should I do?
मैग्नीट्यूड निकालना पड़ेगा सब पोल्स 1 0।
क्या करना पड़ेगा?
मैग्नीट्यूड डेसिबल में।
नहीं, तो इसका एक आसान तरीका है ना, यही तो पोटी प्लॉट में सिखाया गया है। इसका आसान तरीका क्या है? ये सारे, ये दोनों जीरोस हैं यहाँ पे, उसके बाद सारे पोल्स हैं, तो इसको कैसे प्लॉट करना है फटाफट एकदम देखते के साथ? What is the next thing that I should do? How will I plot it? Yeah, Vasanti, you were actually helping me out here. So what should I do next?
Sir, at zeros, the slope, the plot will increase with 20 decibel per decade. Sir, at poles, it will drop by 20 decibel per
Yeah, so
decade.
let's say this
Sir,
is
with
20
that,
decibel per decade. Okay, so this is 20
yes, sir.
dB per decade. Fine, plus 20 dB per decade. All right. Now at this point, what we have hit another zero, right? 4 is also zero.
Sir,
So at this point, it should increase again like this. Oh, this is congested. So I'll probably move. Hmm. Fine. So now this is how much?
sir, 40 decibels per decade will be the slope of that at 4.
Yes, very good. Plus 40 dB per decade, right? This is a slope here. Yes, what should I do next? What happens when it reaches here at this point,
Sir, it will decrease by 20
डिक्रीज
decibels per decade.
-20।
right? So वो कैसा दिखना चाहिए? So इसका slope जो है यहाँ पे ऐसा सा था, right? तो इसके पैरेलल चलेगा, right? The new line will be parallel to the one that I drawn just now, right? It should be like this. Should be like this, right? Right now?
Yes, sir.
Then it reaches this point. Yes. What should happen next at this point? I mean, I have just reduced the slope from 40 dB per decade to 20 dB per decade, right? Each time that it hits a pole, the slope decreases by 20 dB per decade, isn't it? So now that I have hit another pole here at 15, what should happen to the overall slope?
Then it should become zero. It will become flat line.
And yes, it will become a flat line. Very good. Fine. And what happens when I reach this point, the last point, last pole?
So it will decrease minus 20 decibels per decade.
Yes, it will decrease minus 20 dB per decade. So it will be like this, right? So this is minus 20 dB per decade. Very good. So this is the Bode plot, magnitude plot. So how will the phase plot look like? This will be tricky. Phase will be tricky. Tell me, how will the phase plot look like? I just want a rough idea from you, because this will be tricky slightly. Tell me, how will the phase plot look like? Let's make a phase plot. Again, this is omega only, okay? And this is, let's say this is 0. Then we have 90 degree, we have 180 degree, okay? We have what, minus 90 minus 180. Yeah, tell me, how will this look like? You guys remember how to do the phase plots? Yeah, do you guys remember? Anyway, so see, in phase plot, what we do is, here what we do, right at the point where we hit the pole, right at the poles and zeros, only there we change the slope, right? That is where we change the slope. Fine. But for the case of when we draw the phase plots, we draw it, we change the slope 10 times before and 10 times after the poles and zeros. Does it ring a bell? Does this ring a bell to you guys? So let's say this
Yes,
is
sir. Sir,
2.
but why do we take it as 10?
Yeah, that's a very very crude approximation, okay? It actually doesn't happen like that, but it's just a very crude approximation. 10 times
Okay,
is
sir.
actually for 10% error, okay? So it's a very crude approximation. In fact, this also is a very crude approximation, isn't it? It doesn't happen like this. In fact, the actual Bode plot would be very smooth. Okay, let me use a different color. It will actually be starting here, and it will be, sorry, like this. It will move on very smoothly. Okay, it will then move like this, and then it will do this, then it will do this, and then it will move on like this. It will be very smooth. It will not do the sharp turns. It will not make these sharp turns. Okay. So this is not a very good example to explain the way we draw phase plots. I'll just trust you guys. I just say this, that let's say this is the first pole, which is at first 0 at 2. So what we will do is, at 10 times before 2, which is 0.2, isn't it? To find, let's say this is 0.2, omega is equal to 0.2, and 10 times after this, which is omega is equal to 20, right? So since 20 is all the way away from the actual 0, there will be some problems. But let's say you only had one 0, only 2. let's ignore 4, 9, 15 and 20 for the moment. Let's say you only had 2, then in that case 0.2 and 20, these are the two places where you have to worry about. And since it is a 0, what does 0 do? You see, in this case, what will be the this is a 0 which is a left half plane 0, isn't it? This is a LHP 0. uh, so what will happen due to this 0? Will this will this lead to a phase increment, or will this lead to a phase delay, or rather phase decrement? Do you guys understand what I'm saying? Okay, let's take another example. This is not a good example to explain this with. It will simply confuse you. I'll take only one simple pole and 0. So let's say your h of s is s plus 1 plus s by 4, okay, and or rather s by 1, okay, and other one, and the pole is 1 plus s by 20. No, not 20, not good, 100, even more, 1000. Okay, this is what we have: 1 plus s by 1 and 1 plus s by 1000. So Bode plot of this quickly. Yeah, quickly draw the Bode plot. Come on, quick. So what will we have? We have this h of j omega here. Hmm? Right. So here we have to do 20 log of mod of h of j omega, isn't it? And this is as a function of omega. Come on. So what will be the values? So we have one pole at. So what are the pole locations here? What is the pole?
Minus 1000.
Minus 1000. And 0 is at minus 1, right? Good. Vasant, you have a doubt? You have raised your hand.
No, sir, no, sir.
Okay, fine. So yes, we mark the points here, right? 1 and let's say 1000 is somewhere here. Okay, it is not to scale, but just assume that 1000 is here. So how will the plot look like? Again, so we have, and what is the gain at DC? So this is called DC gain. Okay, h of mod of j omega at omega equal to 0 is equal to is called the DC gain. So how much is that DC gain?
Sir, 0 decibels.
0 decibels, right? Very good. Yes. So what will happen is it will start from this point here. And at 1 we have a 0, right? So it will move up. Correct? Till what point? Till it reaches 100,000, sorry, right? And the slope will be 20 dB per decade. And here it reaches, and then it becomes what? Flat, right? It becomes flat, isn't it?
Yes, sir.
So now coming to the phase point. So how will the phase plot look like? Tell me. How do you find phase plot? How do you draw the phase plot? assume that this is 90 degrees, this is 45 degrees, this is 0 degrees, this is minus 45 degree, this is 90 degree, this is 135 degrees. Yeah, how do you do it? So here we have a 0, right? At this point, at 1. So first we find out 1 by 10 and 1 into 10, right? So 1 by 10 is how much? 0.1, right? And 1 into 10 is how much? Just 10, correct? Similarly, at the location of the pole, you do 1000 by 10, which is 100. So 100 is somewhere here, and this is 1000. So, and then you do 1000 into 10, which is 10,000. Okay, this is what we have. Now, how do you draw the phase response? So, did you guys not understand this phase plotting in Bode plot? I think this was explained in the lectures, right? Phase response also. This was covered in the lectures, right? Phase response also. Come on, anyone? This was covered, right?
Yes, sir.
Yeah. So I guess you have not paid attention to that. Fine. So let us do together. Let us do it together. See. So how what is meant by phase responses? We have already, to represent any complex number, we know that we need two things, right? If we are talking about polar representation, we need two things: its magnitude and its angle, right? These two things, if we have, we can say anything about the complex number, isn't it? Now
Yes, sir.
we know that h of s, when s is replaced by j omega, then it becomes a complex number, right? H of s, when s is replaced by j omega, it becomes a complex number, right? It is a complex number. So this complex number will have a magnitude, okay, and it will have a phase. So to completely characterize the transfer function, we need to have both of these, magnitude as well as the angle or phase of this of this transfer function, of this particular thing. Okay, so we have already worked our way for towards finding the magnitude, but we now need to know what is the angle, or rather the phase of this, right? So let's do it first in terms of by writing the expression. So this is h of j omega is equal to how much? Is 1 plus j omega by 1 divided by 1 plus j omega by 1000. This is our h of j omega. So what is the angle of this? What is the phase of h of j omega? How do you find the phase of any complex number?
The tan inverse of imaginary part by real part.
Yeah, good. And if you have a numerator and denominator both, so what do you do?
The sum of the angles of the zeros minus sum of angles of poles.
Very good. No, no, not like that. Yeah, but actually that is correct. But do it. Say it like this. Okay. So angle of h of j omega is equal to sum of phase of all the numerators, angle of all the numerators. Okay. Minus sum of angle of all the denominators. Okay. Let me write it clearly so that it's always there. So different color. Angle of h of j omega is equal to sum of angle of all the numerators minus the sum of angle of all the denominators. Fine. So what you said is also correct, Vasanti. So when you find it, it will actually end up becoming the same thing. So sum of angle of all the zeros minus sum of angle of all the poles. So what will it be? Angle of h of j omega would be tan inverse of, first we have to sum all the numerators, right? Angle of all the numerators. So since we have only one numerator here, right? All the numerator terms, rather the grammar is not correct here, but you understand the emotions behind it, right? So what is the angle of this numerator here? It is tan inverse of
Omega.
imaginary by real, right? So what is the imaginary portion? Omega by 1 divided by, what is the real portion? Only 1,
1.
correct? Minus tan inverse of, again, what is it in the denominator? What is the imaginary part?
Omega by 1000.
Divided by 1, right? This is what it is. Now tell me, when you try to solve this, you know that now this is where you make the approximation. Fine. So tell me something. If you ignore the second term for time being, this guy here, we'll look at both of these individually. Okay. So let's first look at tan inverse of omega by 1, only the first term. Okay. We know that 1 is the 0 here, right? 1 is the 0 here. That is how we have constructed our, sorry, that is how I have written it here. Okay, that 1 is the 0. In this case, 1000 is the pole here, right? So let's look at the first term here, the 0 1. So in this case, let's say if omega is much larger, omega if it is much larger than 1, what happens to the first term? Tan inverse of omega by 1.
It will become 90 degrees.
Yes, very good. So tan inverse this guy here, it will tend to 90 degrees. So let's take a fresh here. So tan inverse of omega by 1 divided by 1 tends to 90 degrees if omega is much greater than 1, right? That is fine. Now what will happen if omega is much less than 1? What will happen?
So it will go to 0.
Yes, it will go to 0 indeed. Very good. That is excellent. Now what happens when omega is exactly equal to 1?
So 45 degrees.
Very good. It is 45 degrees. Fine. Excellent. Now that we are clear on this, the approximation which you make in drawing the phase response in Bode using Bode approximation, what we do it, this omega much greater than 1, how will we assume what is the much greater? I mean, uh, in fact 2 is also greater than 1, okay, 10 is also greater than 1, 1000 is also greater than 1. So where do we make this put this boundary, that it is now that we can say confidently that after exceeding this value, now it has become much greater than 1. So that is where we use the Bode approximation of 10 times. Okay, so if omega is greater than 10 times of whatever 0 or pole you have, okay, so in this case it is 1, then it is much greater. Okay, similarly if omega is less than 1 over 10, then it is much less. Okay, and omega equal to 1 is there is no ambiguity there. Now do you understand? This part is clear? I guess this part is clear. Fine. So all right, now let's come to so this is zeros. Okay, this is for zeros we have. Now let's talk about poles. So pole will always have a subtraction, right? It will always be associated with a minus sign, isn't it? The angle of poles, because they come in the denominator, isn't it? The poles will always be associated with a negative sign. So let me take the negative sign right away. So we will talk about the angle of minus of tan inverse of omega by 1000 divided by 1. Okay, so tell me what happens if again omega is much greater than 1000. What is the angle?
So 90 degrees.
No, it is minus 90
Minus
degrees.
90 degrees.
Yeah, good. Similarly, if omega is much less than 1000, what will the angle be? 0, isn't it? Yeah, and it will be minus 45 degrees if omega is exactly equal to 1000, right? Again, similarly in this case also, what is meant by much greater than? If omega is 10 times greater than 1000, then it is fine, it is much greater than. Similarly, if omega is 10 times less than 1000, then it is again much less than that. Okay, and omega equal to 1000, there is no ambiguity there. So now if you want to construct the phase response, you just have to stitch these things. Okay, so what will you do? First, which is smaller, 1000 or 1? Definitely 1 is smaller, right? So first we will hit 0. Okay, so now that we have put it here, you see what will happen. You see that when omega is less than 1 over 10, which is 0.1, what is the angle? 0, right? 0 degree is the angle due to the numerator, right? And similarly, when omega is actually less than 0, less than 0.1, poles is not even in the picture, right? You're getting my point?
Yes, sir.
Okay, I'll just make this so that this is up till here, right? Up till here, this is the situation. Till 0.1, the angle is 0, okay? Now, after it is 0.1, what happens? After this, you can no longer make the approximation that omega is much less than 1, right? Because now, after 0.1, omega is going to be greater than 1 over 10, fine? So, what will happen is, it will start to increase, right? It will start to increase the angle. Now, where should the angle be? You know that at omega equal to 1, the angle should be exactly equal to 45 degrees, right? Right? So let's reach that point. At this point, the angle is exactly equal to 45 degrees, isn't it? And now, at omega equal to 10, at omega equal to 10, after omega equal to 10, we know that the angle has to be 90 degrees, isn't it? After omega equal to 10. This thing. So, what we'll do it? We'll put, we'll use that and we'll do this. So, at this point, the angle is exactly equal to 90 degrees. Fine. So it's actually in the approximation there is a linear curve like this. There is no curve involved. This goes linearly like this. Is that fine? And after omega equal to 10, it will go on like this, in this way, isn't it? But now, when it hits 100, this point here, what will happen? When it hits 100, what will happen? We have already taken into account numerator, right? But then the phase due to poles will start to come into picture, right? And what will happen is, when it first comes, when it first hits 100 here, what will happen? Up till 100 there is no problem, isn't it? But after 100 its phase will start to decay, right? Its phase will start going towards minus 45, and whatever phase was from there, minus 45 will be added, isn't it? So I'll just write it here. Just tell me whether you understand this or not. So at this point, at 100, there will be a minus 45 degree. After this it will, and from 90 to 90 minus 45 is 45. Okay, so it will start going down from here, and then it will keep on doing that until it reaches omega into 10, omega into 10, after which there will be a minus 90 degree. So 90 minus 90 will be 0. So it will do this, and from here again it will start going to do this. So did you guys understand this?
Yes, sir.
Okay, cool. So I hope this clears your doubts about drawing the phase response. Did it clear the doubts about drawing the phase response? So this was actually a very simple example where where the poles and zeros were far apart. Okay, there will be problems where, I mean, such as this, the earlier example, where 10 times approximation will lead to encroaching the area, and probably in this case it is very simple, right? You understand that in this case we cannot do this beautiful thing, like very simple thing here, because in this case 2 times 10 is equal to 20, and it has encroached all the areas of this, right? You cannot do the simple approximations which we just did here. They will have to add and subtract and all kinds of things. So for these complicated things, you will probably not need to draw it by hand. You will make use of the uh, basically softwares there, which are available online for these complicated things. But you should have the idea, okay, how the Bode approximation is used. So as an exercise, you try to create some Bode plots for different transfer functions. Okay, this will help you understand the concept here, and try to make both the phase response and the try to plot both the phase response as well as the magnitude response. So this is the phase response. All right, so I guess this concludes it. Now where's the 3 dB frequencies looking at the Bode plot? So tell me something. So in this Bode plot, where are the 3 dB frequencies? What is meant by 3 dB frequency?
That the frequency at which the gain becomes half of the maximum value.
Half. 3 dB is half, or is it root 2?
As a root to set magnitude square will become half.
Magnitude square? It is actually 3 dB is actually root 2, right? It's not. Okay, let's do this calculation. What is half? Okay, so let's do this. So 20 log of 1 by 2 or 0.5 is how much? Okay, let's do this calculation. So log of 0.5 into 20 is actually minus 6 dB. Okay, is that okay? I did it right
Yes, sir.
now in my mobile, so I know that this is correct. It is minus 6 dB. Okay, so it the 3 dB frequency has it is actually used because the power actually reduces by half. Okay, because power is magnitude squared. Okay, so that is why power reduces by 2 times. So that is why it is of concern. It is of significance. In terms of magnitude only, the magnitude only goes by root 2 1 over root 2 times. Okay, or rather this. Fine.
Yes, sir.
Ah. So tell me something now. What is the what what I was thinking about? Yeah. So tell me what is where is the 3D frequency? So what do you understand by 3D frequency in that case? Where is the 3D frequency here? So there can be two types of. I mean, in this case, the 3D frequencies. There can be two types of 3D frequency here, right? First of all, let's talk about the center mid-band gain. Okay. So where do you think the mid-band gain is here? In this case, where is the mid-band gain in this figure? Because someone asked me what how to find mid-band gain and all.
Sir, will it be roughly between 9 and 20?
9 and 20. It will be actually between 15 and 20, isn't it? This is the section, right? So mid-band gain means where the gain is generally when it is talked about the mid-band gain, where the gain is flat for a long duration and it is generally maximum. Okay, I mean this is very subjective. Mid-band gain generally means that the place where the gain is flat. Okay, place where gain is flat and it is not equal to 0. Sorry, it is not equal to 1. Place where the gain is flat and it is equal to maximum value. Generally, that is generally the meaning of mid-band gain. But however, you can also have the have this kind of a Bode plot where I mean such a scenario can also come about. Okay, so in this case there is a pole here, then there is a 0 here. Basically there were two poles here, then there was a 0 here, then there was another 0 here, then we have another 0, and then we have two poles again. So in this case this is the mid band gain. Okay, but the gain is actually lower than all of the other gains. This is the mid band gain. So mid band gain, you can say that where all the poles and zeros have hit. I mean somewhere it you can understand it intuitively as the place where which lies in the middle of all the poles and zeros. Okay, like in this case, it is actually lying right in the middle, right, right in the middle where there was all the poles and zeros have hit, and somewhere in the middle where there's a plateauing, there's a flat region, right? You understand this?
Yes, sir.
Okay, so this is the mid-band gain. Now tell me what is the 3 dB frequency. So in this case the 3 dB frequencies, we have two 3 dB frequencies. Okay, in this case we have one 3 dB frequency at this point and another at this point, place where the gain actually drops by minus 3 dB. So in the Bode plot, we cannot show it that the gain has dropped by minus 3 dB, but actually the gain has dropped, right? In the Bode plot, we just assume that the gain at this point is same as the gain as the gain here, right? But actually we know that the gain here will be 3 dB lower, right? So the actual plot would look something like this. Different color. This is the good color. So the actual plot would look something like this, right? Sorry, this is not good. Huh. The actual plot would look something like this. So this is the midband area, okay, and from here it will start to decay like this, and here it will start to decay like this. And if you zoom it, then this is minus 3 dB, isn't it? Similarly, this also is minus 3 dB. So here we have two minus 3 dB frequencies. Okay, do you guys understand? I hope you do. So generally, minus 3 dB frequency is the point uh, where for the first time, or in the midband area, if there is a gain at in the midband area, okay, and from there you have like dropping of minus 3 dB, then you can call as that frequency as minus 3 dB frequency. Okay, you will not encounter such complex kind of Bode plots in real scenario. I mean, this is a very I just made it like this. Okay, you'll not get something like this. You probably would encounter Bode plots of this kind, where there is a band pass response which looks something of this kind. Okay, or probably you have a low pass response which looks something of this kind, or you can even have high pass response which looks something like this. Okay, so here we talk about minus 3 dB frequency is what? It's the place where the gain drops by minus 3 dB. Okay, the frequency where the gain drops by minus 3 dB. Similarly, here in the band pass response, the place where minus 3 dB gain drops by minus 3 dB, that is called minus 3 dB frequency. For band pass response, you will have two frequencies like that. Okay, you will have two frequencies like that. You will have two frequencies like that here, as we saw in this case. So I hope that explains the concept of minus 3 dB frequencies. So this is clear, I guess. This is clear, right? I know I'm in a hurry here, but because that is only because I have not discussed any question today. I only discussed all these things today. So probably I will. If you have any doubt, I'll again come in the next session. Maybe I will again explain these things. So midband gain was also explained. Forming equations for non-ideal op-amp, that is something which we have not talked about. And also, how can we have? Oh, this is also talked about. Right. Oh, finding the midband gain for a large RC network. That is something which you asked me earlier. So, can you give me an instance for an example of a circuit which you were not able to solve? Large RC circuit thing. I guess Vasanti asked me this question, right?
Yes, sir. Sir, that was actually a part of week 3, sir, in which like we had a huge RC network, like maybe the internal circuitry of MOSFET. That's what the professor said in one of the videos.
Okay, I'll look at it. Okay, in week 3, I'll look at it and then explain you. Or
Yes, sir. Yes,
probably I
sir.
will look at it just now. Okay, give me a second. Mm, week 3 you said, right? So
Sir,
let's
lecture
see.
2.
Lecture 2, module frequency response example.
Yes, sir. Yes, sir.
Okay. Miller's
Sir, little
theorem.
more ahead.
Here,
Is that this one?
this one.
Yes, sir.
Okay, okay. We'll come to it. Okay, in the next session, we'll definitely talk about it. Don't worry about it.
Yes, sir.
Ha. Today let's stick to this. Forming equation of non-ideal op amps. Let's solve a problem. Okay, on that. Ha. So this is a good example. Let's just do it. In this case, the only non-ideality which I have added in this question is that the gain is finite. The gain is not infinite, okay? The gain is finite here. AB is equal to 40 dB. So what is that in terms of actual number?
Sir, 100.
Yes. Yes. So in that case, what will be the, yeah, now let's solve the question here. So what is the question? The question is find the gain V0 by V in. So let's do it. We have an op amp in our case here. This is minus, this is plus. We have hmm. So let's say if the gain AV had been infinite, so what would have been the value V0 here? How do you find it?
Sir, minus
Oh,
RF
by
by
the way,
R1.
there. Oh, I have important thing I have missed here. Okay, yeah. How do you do it in that case? So this becomes an ideal op amp, right? In that scenario. So how do you solve for an ideal op amp? You say that this voltage here is zero, right? Because of virtual short, isn't it? Virtual short between these 2 points. You can say that this voltage is zero. After that, you say that you equate the current going into here and this point, right? You do that, and then you find the voltage. So you do this, the current actually goes here, so you say that it is V in. What is the current? V in upon R1 has to be equal to how much? 0 minus V0 upon RF, which becomes, so that V0 by V in is equal to minus RF by Rn, R1, right now. This is what you do for when you get an ideal op amp. So when you have a non-ideal op amp, there also you do the same thing. So in this case we have only assumed one non-ideality, that the gain AV is not infinite. So let me just copy and just solve it again. Here you cannot assume that the nodes are at virtual short, okay? That virtual short thing, that approximation is valid only as long as the gain is infinite. But in this case the gain is finite, right? The gain is actually equal to 100. It's a finite number. So there will be some difference between these two. I mean the this voltage here, let's assume this is equal to V1, okay? This will be some finite number. This will not be 0. This will be some a non-zero number, V1 value. This will be some non-zero value. So, but still, you know that the current that is going to come here, it cannot go inside op amp, right? Because we have assumed only one non-ideality. There is no current which is going to come into this, right? So the current here is actually 0, right now. So if you are understanding, just keep saying something that you understand. Otherwise, I'll keep explaining again and again. Fine. So in that case, what we can do is we do the same thing. The current that is going to come from V in is goes up like this and it moves completely out into RF. Okay. Since none of the current is going here, so we do the same thing. but it's just that now we have another, oh sorry, we have another parameter to deal with. Now we cannot just assume that v1 is equal to 0. We have to assume that v1 is non-zero. So after that, how do we form the equations? We do it like this. What is the current? What is this current? Let's call it IR1. Let's call it IR1. What is IR1 in terms of V in and V1? So IR1 is equal to V in minus V1 upon R1, right? This is IR1. And the same IR1 flows here also, right? Through RF. So what is current through RF? This will be equal to how much? The current through RF. So what will be the current through RF? V1 minus V0 upon RF, right? That is fine, right? Now, yes. Now we have two unknowns, right? We have V1. We want to find out what is V0 by V in, right? But we have an unknown here, V1. So first let's solve this. V in by R1 plus is equal to V, alright, plus V0 by RF equal to V1 upon 1 by R1 plus 1 by RF, right? This is what we have. So this is our equation 1. Now we have a problem here, right? We have an unknown here, V1. We do not know what is V1, but we want to without finding V1 we will not be able to find the relationship V0 by V in. So how do we find out V1?
Sir, we have the gain given. The 100 is
Yes,
equal to VO by
yes,
0
yes,
minus
exactly,
V1.
exactly, exactly, exactly. Very good, very good. So by using the definition or property of the op amp, we have how much? V1, or rather 0, because it is plus minus negative, right? So 0 minus V1 into AB has to be equal to V out, right? So it is
Yes,
equal
sir.
to minus AB times V1, that should be equal to V0. And what is AB? It is minus 100 times V1 equal to V0. So what is V0 V1 in terms of V0? So V1 equal to
Minus V0 by
minus
100.
V0 by 100. Very good. So now this is the second equation. So now we will simply replace this one here. Okay. So what do we get? Using 1 and 2, we get what? So we have V in by R1 plus V0 by RF, and that is equal to V1 is what? Minus V0 by 100 into 1 over R1 plus 1 over RF. Now just we have to collect the terms, right? So V in upon R1 should be equal to minus of V0, okay, 1 by RF plus 1 by 100 times 1 by R1 plus 1 by RF. Isn't it? Is this fine?
Yes, sir.
V0 by V, how much is that? Yeah, so when you solve it, this will look like okay, let's solve this. So okay, this will be 1 by RF plus, this will be R1 plus RF divided by 100 times R1 RF, right? And this will be how much? So 1 by RF, if we take outside, we take, so this will become minus RF by R1, okay, and this will be 1 divided by, I've taken RF outside, so this will become 1 plus 1 by RF outside, so this becomes 1 plus RF plus R1 upon 100 times R1, isn't it? Is this fine?
Yes, sir.
So in this is very obvious that if in this case, if this 100 was what? 100 was AB, right? So if AB becomes, instead of 100, if it becomes 1000 or 10,000, let's say if it instead of 100 it becomes infinity, what will happen? So
So
if
the gain will become minus RF by R1.
yeah, if AB tends to infinity, then from this example also we can see that the gain V0 by V in will be equal to minus RF by R1, right? So this is what we got earlier, right? This is what we got earlier. So this is actually correct, right? This makes sense. This is a good sanity check, isn't it? So I guess now you understand how to form equations in case we have a non-ideal circuit. We just let's say in terms of, so here we discussed one non-ideality, okay? Let's say we have another non-ideality also. Let's say that this also takes up some current, I maybe some I op amp, okay? So then how will you deal with this? Let's say I mean, other than the AV being equal to 100, not equal to infinity, it also has another non-ideality where the current also goes into the op amp. There is some input current, input bias current required. So then how will you do it? How will you solve this? Come on, try. You don't have to solve it here, just give me some inputs. How will you solve? What will be your approach here?
Sir, we can apply current law, Kirchhoff's
Hmm.
current law.
Correct. So what we did here was we simply assumed. I mean, we know that the current was not going inside, so that is why whatever current IR1 was coming due to flowing into R1, we said that the same current should flow into RF also, right? But here, what will happen? In this case, there will be other paths also, right? There will be this current, there will be this current, and then there will be this current. So what will happen is that this current will be equal to the sum of these two, right? That is one other equation that you will have, other than AB, this relationship. Other than the property of the op amp, you will also have another equation that will come from the Kirchhoff's current law, right? So then you can solve the question, solve the circuit here. Is that fine? Did you guys understand how to form equations? संकेत, आपका सवाल था ना ये, इक्वेशंस कैसे फॉर्म करने हैं अगर नॉन आइडियल सर्किट हो तो? संकेत, आपको समझ आया क्या? आपकी आवाज नहीं आ रही मेरे को. अगर आप समझ गए तो प्लीज थम्स अप कर दीजिएगा, वरना मेरे को फिर से समझाना होगा. और प्रोबब्ली आप कमेंट. ओके ओके, थैंक यू थैंक यू. Let's see whether I should discuss any other thing. Alright, this is not required, not needed. Yeah, in this question we have another non-ideality, okay? Here we have non-ideality in terms of offset voltage. So how do you deal with offset voltage? I have not talked about it. The offset voltage is another non-ideality. The way we deal with it is we assume, just to model it. Okay, let's say I have an op amp here, and there is some offset voltage V offset. Let's say it is equal to some 10 millivolts. Okay, let's say this is the offset voltage. And what is meant by offset voltage? This V plus and V minus, between, if you, even if you connect them together, even if you connect them together externally, still there will be some due to some manufacturing defect, they will not internally, there will be some mismatch between their voltages. Okay, I hope you understood that much from the lectures. Offset voltage, right?
Yes, sir.
Huh. So even if you connect them externally using wire, there will still be some voltage difference between the two terminals. So the way to model it is not actually how it is done, but I mean, what I'm going to say next is not actually how the real circuit would look like. It is just that we have made some, it is just to put it on pen and paper, okay? Just to put it on paper, that is the way that we model it. How we do it is, we assume that uh, there is some voltage connected to either one of the terminal. Okay, like in this case, you see, uh, okay, what we'll do is, let's assume that there is a 10 millivolt of offset. Okay, so what we'll do is, we'll probably put a voltage source here, which is equal to 10 millivolts. Okay, so it means that even if you connect, sorry, it will be like this, and this will be V plus. Okay, and the terminals that are accessible to you is outside of this box. This is just for modeling. Okay, this is not how the actual circuit would look like on board, on your when you see it, look it with your naked eyes. It will not look like this. It will not look like this, but it's just to model it. So what it means is, even if you connect it externally using this wires, you still have a 10 millivolt of difference between the input terminals, isn't it? We have modeled it like this, modeled it. Do you get my point now? This is just
Yes,
for
sir.
modeling purpose. And in that, when you apply external, when you model the offset using this voltage source, then you assume that this op amp does not have any offset. Okay, this op amp is ideal in terms of offset voltage. Okay, so this is what has been done here. In this case, we have an offset voltage of 50 millivolts. Okay, and that offset voltage is being modeled by adding a series voltage source to the plus terminal. Okay, and when you have already modeled this, then you assume that this op amp here is ideal in terms of offset voltage. It may have some another non-idealities, like if it also had a finite gain non-ideality, then there would be that finite gain non-ideality. Since in this question there is there is no such information given, we'll assume that the gain is here equal to infinity. Okay, so tell me, quickly solve this. If the offset voltage is equal to 50 volts here, 50 millivolts here, tell me what will be the V out here. The AV gain here is infinity. Come on, quickly solve this. Why is everyone so quiet?
Sir, but here V in is 0.
Yeah, V in is 0, right? I know. So what? You still have a voltage source here, right? See, what I've told you is that even if you connect it, okay, even if you short it, so in this example also you see that in this case ideally the Vin is 0, right? Because you have shorted the two ends of the op amp. So ideally what should have happened? The output should have been 0, right? In this case ideally. But because of the offset voltage, this offset of 10 millivolts, the output will not be 0, right? It will be non-zero value. Is that making sense?
Yes, sir. Yes, sir. Yes, sir.
Similarly, similarly, in this case also, this op amp is non-ideal, okay? And what is the non-ideality in this op amp? There is an offset voltage in between the inputs, okay? Now that offset voltage here is being taken out and modeled outside of this op amp, okay? This offset here, it doesn't appear like this voltage source has been placed here. This is just for our convenience that we have taken the voltage source outside, offset voltage outside, and represented it in terms of a dedicated voltage source, okay? So now even if the Vin is 0, you know that there will be some voltage, right, at the output.
Yes, sir.
And how much that would be?
Sir, I got output voltage as 9 volt.
Okay, let's see. So this is 50 millivolt, right? Because of virtual short, because AV is assumed to be infinity, right? And RF is how much? 18 kilo ohms. So we have th- 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 this current and this current has to be same, right? So 50 millivolt upon R1 has to be equal to V0 minus 50 millivolt, right? 50 millivolt 50 millivolt upon R1 has to be equal to V0 minus 50 millivolt upon RF, right? So how much will that be? V0 by RF is equal to 50 millivolt 1 by R1 plus 1 by RF. So V0 equal to R1 plus RF divided by R1 into 50 millivolts. So it is the famous 1 plus RF by R1 times 50 millivolt. So what is the values? RF is 18 kilo ohms, right? 1 plus 18 kilo ohms divided by 2 kilo ohms. So how much is that? 10 into 50, right? So it is 500 millivolts. So probably you did some calculation mistake. How much did you get?
Sir, I got 9 volt.
No, that doesn't look correct. I mean, this is right? Whatever I have solved, there is no
Yes,
mistake here,
sir.
right? So probably you did some calculation error. So just check it, okay? Yeah. So if there is no, so this question is actually straight away asked from the lectures. If there is no internal correction of the circuit in figure 2, what can be done externally to reduce the effects of offset voltage? So you remember something about adding a capacitor to reduce the effect of offset voltage? Do you remember something like that? Was taught in the lectures. If you remember, it's good. If you do not, just go and brush it up. Okay. So this is straight away taken from the lectures. I have some more questions to discuss. So this I have discussed in fair detail. Okay, how to make Bode plots and all. So probably you do not need to worry about it because I have discussed in detail. So don't need to worry about it. Yeah. So the thing that I was explaining earlier, 3 dB frequency. You see, right at the place where. Okay. Right at the place where the pole hits for the first time, that is the 3 dB frequency. Okay, so this is the 3 dB frequency 1. There are three poles, 1, 10 and 100, right? So it first hits at 1. So at this point we have a pole, and at this point only there will be minus 3 dB. So I'll not discuss it today. I mean, I don't think we need to discuss it because I have already explained a lot about it, about Bode plot and all. So you don't need to worry about it. Try to solve these questions on your own, okay? These slides will be shared with you. Try to solve these questions on your own. I hope you will be able to solve them. Since the time is up, I'll probably meet you next time with some new questions, and if you have any doubt you can ask me, okay? So I guess that's it. We'll again meet next time on Tuesday, okay? So this is the only
Thank
time
you,
that we
sir.
have met on Saturday. संकेत, आपको कोई क्वेश्चन पूछना है? संकेत, आपने हाथ, हाँ, व्हाट इज योर क्वेश्चन? आपका क्वेश्चन क्या है?